Okay. Who's going to make an announcement? Okay. Good morning, everybody. So today we have the pleasure to have here Radu ROIBAN from Penn State, who's visiting ETH this year, and we managed to get at least him for 1 week. So Radu, for those who don't know Radu already, he's an expert on scattering amplitudes. He has been in the field, leading the field for many years, since the integrability times up to now, where many of us moved to gravitational-wave physics, and indeed today he's gonna give a colloquium about how quantum scattering amplitudes can help with precision gravitational wave physics. So Radu, the floor is yours.
Thank you very much. Thank you very much for the kind introduction and for the invitation to visit IPhT for an extended amount of time. So this colloquium is based on a number of pieces of work done with a collection of wonderful collaborators whom I've listed here, and some of whom are right here. So about 110 years ago, Einstein gave us the general theory of relativity. And shortly thereafter, there were some predictions coming out of it, and they had to do with gravitational waves. That was essentially the first prediction, actually. Now, if you start counting dimensions, it turns out that detecting these things directly is particularly difficult, just because the amount of power that is being emitted in gravitational waves is really tiny. For example, the Earth-Sun system emits about as much power as a fifth of the power that we need today for this, to power the projector. If we go a little bit further out to the closest stellar binary, it emits quite a bit less than a small nuclear reactor on Earth. So anyway, the distance is pretty large. The amount of power reaching us is really tiny. And the thing that we actually measure are really displacements. And the dimensionless displacement corresponding to this closest stellar binary is about 10 to the minus 23. So measuring such differential displacement is really would be a remarkable achievement, technical achievement at the very least. And that achievement has, in fact, been achieved about 10 years or so ago. and almost to the day after Einstein's prediction of gravitational waves, LIGO reported a measurement which looked like this, which we referred to as the waveform, which is essentially the signal coming from a coalescing binary system. One might go as far as say that we have seen a graviton, and this is how it looks. All right. So this was 10 years ago. So 10 years later, a few upgrades and a few detectors later, we have a little over about 300 or so detections, all of which fit general relativity to the best of our understanding. So to a large extent, one can say that the field has moved from detection stage to a precision stage. We have 300 odd events, so some kind of statistics can be attempted. And there is, so the gravitational wave observations did indeed open a new window in our universe, and there are a number of physics goals that one might set to achieve through this window, such as study general relativity in the strong field regime, study black hole properties, study extensions of general relativity, study, I don't know, microstates of black holes, and so on and so forth. Now, this is from a very practical point of view, from where some of us here are theorists. Are there any experimentalists here, if I might ask? Okay, we're all theorists. So as theorists, we can set our crosshairs on something to do, such as develop new tools to help our experimental colleagues in their endeavor of studying all of these. And we have quantum field theory tools that have not been used in this context, so we might want to try to use some of them. So now this is the status today as far as observations, 300 or so events. Now, future is particularly bright in gravitational waves. There will be new ground-based detectors, which are more precise by a couple of orders of magnitude. There will be space-based detectors, which will observe signals that are very, very long. So we have to, as theorists, we have to accommodate and make predictions to cover these. The fact that the signals will be very precise means that our accuracy has to increase. The theoretical precision and accuracy, has to increase. The fact that the signals are very long means that our accuracy should be good enough to not degrade over an evolution time of a few months or a few years. Therefore, that means that the theoretical precision has to actually be very precise. So the typical approach to theoretical predictions, or at least the go-to approach, one might think is just solving Einstein's equations. And of course, we can't solve them analytically. There has been remarkable success about 20 years ago, when Pretorius first solved Einstein's equations for a pair of black holes, in spiraling black holes. However, there is, since it's a numerical calculation, one has to do this one set of parameters at a time. And each of these things takes about, I don't know, 100,000 CPU hours. So it's not something that can be done instantly. And moreover, data analysis and parameter estimation requires a huge number of such solutions. For example, the first detection used about 250,000 such solutions. Now, as it turns out, the grand total today of such solutions is about 3,756 black hole simulations. So you might wonder exactly what gives this number versus this number. Where is the difference coming from? Well, the difference comes from models. So these models are sometimes called surrogates, which essentially take numerical relativity data and interpolate them. There are phenomenological models which model certain regions of parameter space. Then there are physics-inspired models, perhaps the widest known of them being the effective one-body theory, which takes as physics input a two-body Hamiltonian for point-like particles, finite size corrections in differential energy and angular momentum laws, and turns that into predictions. And perhaps more recently, there is a machine learning effort. So this is the slew of models and the slew of methods that people have used ever since the beginning to actually produce the waveforms, waveform templates actually, that are used for data analysis. Now, the Einstein Telescope collaboration pronounced that more effort needs to be put into analytic waveforms and analytic calculations, just because doing everything numerically is so slow. And of course, this is the target, I should say, I never said the target. The target time for generating one such waveform is about 50 milliseconds. So, since we want analytics and we are theorists, and we can solve the equations analytically, well, we have one option, right? It's the spherical cow. We have to use perturbation theory of some sort. There are three versions. Post-Newtonian perturbation theory, which is essentially modeled around, it sort of uses the fact that it perturbs around the circular orbit in which the velocity and this particular combination of Newton's constant and the radius they're all small. There's post-Minkowskian approximation, which will be the focus today, and then there is the small mass ratio expansion, otherwise known as the gravitational self force, in which the velocity and the Newton's constant are accounted for exactly, but one expands in the mass ratio of the two bodies. Okay, now this is perturbation theory, but perturbation theory always takes us so far as it happens in QCD. So to actually go beyond perturbation theory, one needs to resum, and the effective one-body theory is such a resummation method. But then, of course, there are other resummation methods. Perhaps the best known of them has been known since time immemorial. Solving classical equations of motion is a resummation method. But there are also quantum field theory methods, such as resummation of IR divergences, RG, and so on, which start making their way into this particular business, though perhaps not as widely as they should for the time being. And last but not least, there is also a curious approach, which turns out to be very successful, which amounts to stitching together predictions in various regions of parameter space while making sure that they are consistent in the overlap. All right, so perturbation theory, where are we? The status is as follows. It's at least for spinless bodies. It's captured by this chart. Post-Newtonian, I should say the status is in fact correlated with what we're aiming for. So I was saying a little bit earlier that experimental precision will be 2 orders of magnitude better than the current one. So one might want to translate that into a measure in perturbation theory to know what we're aiming for. And this turns out to be difficult, and it is also dependent on the position, on the region in parameter space where we are. But the idea is that roughly 2 orders in perturbation theory beyond what we know today is the target. So where we are today is in post-Newtonian approximation, everything is known up to 4pn order. So that's v to the 8 and g to the 7 and going on the vertical. Sorry, g to the 5th and going on the vertical. At 5pn, there is all the pieces are claimed to be known. They are just not put together. So the target would be to complete the next couple of columns. And of course, this, the results captured by this chart have been obtained by lots and lots of people over many years, some of whom are in this area, though not in this room. Now, as we go to a post-Minkowskian approach in which the velocity is taken into account exactly, what is known is the horizontal lines. So g to the 4th is known exactly. G to the 5th is mostly known. There are pieces missing, and we're going to get back to that. And we might want to target the g to the 6th and perhaps g to the 7. I should say this g literally counts orders in perturbation theory, so in the usual field theory approach, so field theory counting. So this is 1 loop, 2 loops, 3 loops, 4 loops, 5 loops, 6 loops. So this is no mean feat to actually go down this chart. All right, so Now, how are we doing this? Again, given that the only way to solve Einstein's equations is numerics, and since the approach based on Einstein's equations has been explored at length by these people, we are taking a somewhat more scenic route and use quantum field theory methods. That is, instead of Einstein's equations, we use Feynman diagrams of sorts. So in this approach, the main character is the graviton, which is a fluctuation of the metric around Minkowski space in this case, but one might consider also changing this space to changing the base space, Minkowski, to be something else. This is, of course, an approach that's suited for perturbation theory and questions in asymptotically flat spacetimes. So this is, in a sense, it's ready-made for relativistic gravitational wave physics with relatively compact sources, but it is not suited for questions that are much different from this. Another interesting part about this approach is that it's complementary to a geometric and Einstein equation-based approach. And by and large, it avoids a number of coordinate choice issues, though not all of them, and we're going to get back to that. And last but not least, it makes contact with particle physics and methods that have been developed sometimes here over many years, and we can use that to our advantage. Now, whenever I say scattering in the context of gravity, I'm told that this is a very esoteric thing. But I would like to posit that scattering has been, in fact, one of the cornerstones of our test of GR, basically ever since Einstein gave us GR. Anybody cares to argue with that? All right, good. Because there it is. It is not gravitational scattering of matter particles, but it's gravitational scattering of light. And as it was known back then, deflection of light. Of course, if we take our usual perspective on deflection of light and gravitational lensing is the point of view of the target in a Rutherford experiment. But if we were, powerful beings and we could travel outside our galaxy for a while, then scattering of light would look more or less like this. So this is literally a Rutherford type experiment, again, with light or gamma rays. All right, so scattering is not such an esoteric thing. And as it turns out, the fact that the potential of a scattering-based approach to gravitational wave physics has been appreciated early on by people like Alessandra Bonanno and Thibaut Damour in talks given and papers written or given in 2017 or so. They pointed out that scattering amplitude methods could, in fact, be used to make progress in gravitational wave physics. And as it turns out, quite a few years later, so 7 years later, the Einstein Telescope collaboration acknowledged that indeed this approach was successful in the sense that QFT-based approaches brought both conceptual and clarity and hard results in certain areas. Okay, so with having said this, let me try to explain a little bit more why scattering is useful, and perhaps you have some worries that I would like to try to dispel at the moment. So why should we worry about scattering when the most abundant sources in the universe are bound systems? Well, first of all, it's because we can, and we are theorists, so we can. But not only that, but at some level, scattering and bound motion are governed essentially by the same Hamiltonian, with emphasis on the word essential, which will come back in about 20 minutes or so. Also, scattering, if we care about comparison with other methods, scattering is numerically clean, and it's almost free of gauge artifacts because everything is fixed at infinity. So one shouldn't worry about gauge transformations that fall off sufficiently fast not to affect infinity. Those that do affect infinity, those are captured by the almost of this sentence. Right, so why point particles? Because we typically scatter point particles in quantum field theory. Well, that's because if particles are sufficiently far enough, then they can be approximated by point particles. And one could correct that as they get closer together via some multiple expansion. Why relativistic? Well, because you know, we are talking about big floppy things like you know, neutron stars and so, but they can nevertheless move really speedily if they are, for example, on elliptic trajectories and and they get really close to their companion. And last but not least, why take a quantum approach when everything is classical? And that's because, as it turns out, we get to use in class. We usually don't think about unitarity or conservation of probability in classical calculations. But if we did, and it turns out that it would simplify our lives a little bit more. So these are some of the whys for for a quantum field theory-based approach to classical physics. I still have to tell you how to get to classical physics out of quantum physics, but that's the next step. So let me pause here for a second or two and see if there are any questions. Yes.
So from the scattering approach, you can predict or reconstruct this orbit?
I wish I could. The answer is probably not, but with a lot of effort, some approximation to it, it may be possible. I'm happy to explain a lot more what you know.
So you mean you will embed the scattering results into more?
Yeah, we're going to see in a second one possible approach, but the idea is to construct, or at least an idea is to construct a Hamiltonian from scattering, and then feed it, perhaps either use it as, you know, by itself, or feed it through an effective one-body theory and derive an orbit that looks closed. More questions? All right, so quantum, classical out of quantum. So in quantum field theory courses, we usually hear that classical physics emerges as we take h bar to 0, and in this limit, only 3-level amplitudes survive. And that's sort of true, but it's not entirely true because h bar is dimensionful, so one has to specify also clearly what happens to the other dimensionful parameters. Now, if you ever interacted with Misha Schiffman, you will learn that saying, I want to send h bar to 0 is a really bad idea. You will hear, but h bar is 1, so what do you mean you send 1 to 0? Say it in a different way. So anyway, Misha is not here. Nevertheless, I took to heart his advice. So I like to think about the classical limit as in the sense of Bohr's correspondence principle rather than h bar to 0. And just to make things clear, h bar is 1. Right? Everything on this slide and everything that follows, h bar is 1. So in the sense of Bohr's correspondence principle, classical limit is the limit in which conserved charges like masses, momenta, angular momenta, spins, and whatnot, they are large. And you can work back from this statement and conclude that in this limit, the de Broglie wavelength of the various particles carrying these charges are a lot tinier than the particles, than the size of the bodies carrying this charge, and also the separation. The size comes in via the spin. I should say this is somewhat analogous in spirit with stuff that has been done with semi-classical strings in the context of the ADS-CFT correspondence. Now, as it turns out, this limit reaches inside loop amplitudes and declares that some pieces of loop amplitudes are in fact classical. And this is in fact consistent with the fact that most classical observables, even in Newtonian gravity, are non-trivial functions of the coupling. So if everything came out of trees, then the dependence on the coupling would be really, really simple. So again, just to stress, the classical limit picks out certain terms in the from loop amplitudes and calls them classical. And because we end up needing loop amplitudes, then modern quantum field theory methods are essential. And here is a short list of them, some of them developed here or thereabout. And I should also stress that now these are very powerful. If you combine these methods with the idea of classical limit, and in this particular sense, then they become even more powerful. So we can do in QCD, one can do you know, a couple of loops with a lot of effort. One can do perhaps you know, beginning of 3-loop calculations. Whereas here we can do in gravity, we can do 4 loops with a fair amount of effort. But we will be getting to that. All right, so these are methods. This is what we do. This is roughly how we do it. I didn't quite tell you how we do it, but this is morally what we do. So now, what do we actually want to compute? There are lots of observables one could care for. For example, one could care directly about the waveform, which is what gravitational wave observatories would be seeing. From a theoretical point of view, one could think about scattering angles, final state correlators, and whatnot. There is a long list here. But if one is also interested, at least with current methods, into resummation, then perhaps aiming for something that contains all of them at once might in fact be more profitable, and that would be a Hamiltonian. Now, observables tend to be gauge independent. Hamiltonians tend to be gauge dependent. Yes, we are taking a step back, but hopefully with a step back we can go 2 steps forward. Also, constructing this Hamiltonian, one could also go backwards. For example, compute waveforms, compute these observables, and then invent a Hamiltonian that reproduces them, and that would be a path to constructing this Hamiltonian. So we want to compute Hamiltonians. How do we compute Hamiltonians from scattering? Well, this is a problem that at least morally was solved 100 and some years ago in the beginnings of quantum mechanics. So there we construct, in the case of potential scattering, we construct an S-matrix from the Hamiltonian by solving Schrödinger's equation. To first approximation, the potential is just the inverse Fourier transform of the scattering amplitude. Now, as it turns out, if the potential and the scattering amplitudes depend on a small parameter, then the story is more complicated. The scattering amplitude is a series, is a sum of terms that involve various pieces in the potential. Therefore, the inverse transform of this is also a sum of pieces. Now, in the case of classical gravity, this little g that appears here is Newton's constant, and this v that appears there is various powers of 1 over r, correlated with the powers of Newton's constant. Basically, you can read this as g over r is Newton's potential, therefore it's classical, therefore any power of it is classical, and this is what determines the power of r in Vn. And in momentum space, one aims for this particular dependence on the momentum transfer, which is the Fourier transform of 1 over r. All right, so I spoke for, I don't know how much, 20 some minutes. I said the word scattering amplitudes probably 100 times, but I have not shown you a single one. So here is one. So it's perhaps the simplest one there is, a 3-level 2-to-2 scattering, but it will prove the point that one could use them, or one could use scattering amplitudes to determine Hamiltonians. So just from Feynman rules, so this is the top vertex is the stress tensor of a matter particle with momentum p2. Lower vertex is the stress tensor of a matter particle with momentum p1, and the masses m2 and m1. So just connecting them with a graviton propagator produces an expression of this type, where I kept only the dependence on the momentum transfer q. Here is q that qualifies here. So n equals 1. We want n equals 1. Therefore, n has to be 1, so it has to be 1 over g. I didn't tell you what this log q is. It doesn't matter, but you can ask me later. Right, so, I should say these terms that are here, O of q to the 0, which are in fact independent of q, they're not some esoteric gravitational thing. We encounter them also in QED, or we encounter them in the interaction of electrons, and they contribute, in the case of electromagnetic interactions, they contribute to the spectrum of the hydrogen atom, and we know them under the name of Darwin terms. They are things that are localized at the location of the nucleus. And there is something similar here, just these are the gravitational version of them. Anyway, so this is the S-matrix element, the leading order. This is the Hamiltonian that we're aiming for. So the leading term, V1, is the Fourier transform of the potential of the scattering of the S-matrix. and it is this one. U1 and U2 are velocities. And if one expands this, there are 4 velocities. If one expands this around static masses, then to leading order, one finds Newton's potential, including the sign. So we're not really causing a revolution here. It's still, gravity is still attractive. And then the next order, V square, is a piece of the Einstein-Infeld-Hoffmann potential. And then it continues all the way to V to infinity, because there is a dependence on the gamma factor here. But anyway, this is the fully relativistic generalization of Newton's potential, derived essentially in 3 lines. All right, so this is essentially, you can think of it as a non-relativistic quantum mechanics application. But the same ideas work in field theory. All we have to do is make sure that we organize the relation between potentials and S-matrix elements the right way. And this is done by an effective field theory that contains only the positive energy matter particles, just because we want to scatter, I don't know, black holes, not anti-black holes. And an ansatz for a potential that has exactly the structure that we care for. So it's here, this one. And then the connection between the Lagrangian of this effective field theory and the actual two-body potential is, you just read it off from here, but the argument has to do with the usual connection between field theory and Schrödinger's equation. So the idea is we compute S-matrix elements in a full theory, which is GR plus matter fields. We compute S-matrix elements in this effective field theory with ansatz potential. We set them equal because we want to capture the same physics, and from there we read off the potential. So all in all, we need to learn how to compute scattering amplitudes efficiently if we want to go to sufficiently high loop order. Now, I will not teach you how to compute scattering amplitudes, because that's a much more complicated and a much longer enterprise, and I can't do it justice in a couple of minutes, but the idea is simple. The efficient way to do it is to make use of the singularity structure of the integrands of S-matrix elements, and construct them from a priori knowledge of the location of the poles and residues. This and the corresponding residues. This, I should stress, this is quite similar in spirit with what's going on in integrable models when one constructs various equations or various objects like the S-matrix sometimes based on the singularity structure and the cut structure of that object. Okay, so these methods have been extremely powerful, and they led to a number of milestone calculations, some of them achieved here. And in the Paris area. And we are going to use these methods for gravitational waves. Now, I would be remiss if I say that this is all there is, because there isn't. There are further methods that have been developed specifically for classical calculations, and they involve world lines. So in that case, the idea is one starts with an action of this type, point particles on a world line interacting via gravity, and expands the world lines via around a straight line motion. And then by computing one-point functions in this particular theory of various quantities, such as this fluctuation or the derivative of this fluctuation, or perhaps of the metric tensor, then one finds the impulse that's being exchanged between particles, or the gravitation or the waveform that is being emitted in a scattering process. Anyway, so this is another approach to the same problem, which was pioneered by these guys. And one can use either one of these to obtain essentially almost anything one needs. So we computed the classical parts of, I showed you the 3-level, 1-loop, 2-loop, and 3-loop amplitudes, and we constructed this Hamiltonian, which looks roughly like this. Now, this is a complicated slide, I have to say, and I'm not expecting you to remember anything out of it, other than the fact that it all fits on one slide. And now I have to stress that this is the result of three-loop calculations in general relativity. So just because of that, you can conclude that it's a lot simpler than anyone would have the right to expect. Right? If you think of how 4-particle S-matrix elements in I don't know, even n equals 4 super Young Mills look like, they are a lot more complicated than this. Anyway, the other thing that I would like to emphasize is that the kinds of functions that appear here, they are relatively simple. I haven't shown you what these m's are here, but they contain dialogues and elliptic integrals. But the point I'm trying to make is that in the process of getting here, there are substantially more complicated functions that have appeared and they somehow have canceled. It's not entirely clear why they canceled, but they cancel anyway, and we would like to learn how to predict what cancels and how to actually make use of that particular, of this fact. Now, as far as we can tell, these Hamiltonians are correct because observables constructed out of them reproduce PN results. They have been constructed also by other means and independently, and they have also been extended to include radiation contributions, and we're going to get to that in a second. Now, the corresponding Hamiltonian, the next order, is largely available, and we're going to get to that in a little bit. And hopefully, when we get to that, it will be hopefully clear why I'm not including it in this list. Anyway, so I was advertising this as a very good thing. So we started with the idea that we do these calculations because we want more precision. So with stuff in hand, we can proceed and test this idea of precision. And indeed, such a test was carried out some time ago. What you see on these plots are results for numerical relativity for the scattering of two particles. The numerical relativity are the black dots. And then various successive approximations relative to 3-level, 1-loop, 2-loop, and so on, which are either not resummed in the dashed lines or resummed in the solid lines. So the resummation of the 3-loop prediction of the observables based on the 3-loop Hamiltonian are this blue line here that goes essentially through the black dots. Now, if you zoom in, the error is essentially 1%. So this is still pretty good, right? So the things to emphasize here is that resummation is critical to compare with numerical relativity, and also that what we're doing actually has teeth. It actually produces hard predictions because it helps with matching numerical relativity. So this gives us motivation to proceed to higher orders. Now, this is about the scattering angle. This is not something that, I mean, as theorists, we can talk about scattering angles all we want, and we understand what it means, but nobody can actually measure a scattering angle of black holes in our lifetime. So, but people can observe gravitational waves hitting the Earth because of such scattering events. And there is a formalism developed here that can be used to compute these. And we, as well as my kind chairman and his collaborators at the time, computed this gravitational wave at next to leading order. The leading order has been known for quite a while from field theory methods, and also from quite a longer while from GR methods. So what I'm showing you here is the leading order and the next to leading order prediction for one particular polarization of the gravitational wave, the so-called cross polarization that messes with the angle between the coordinate axes. So what you see here, this is the celestial sphere viewed from outside, and the colors represent the angle of the of two initially orthogonal vectors. So orthogonality is green, and red and blue are different angles. So things start orthogonal before the scattering, and then as the gravitational wave passes by and these things got out of phase, there is something that happens. after the gravitational wave passed, there is this colorful picture that survives, and that goes by the name of the gravitational wave memory. That is a permanent displacement of test masses because of the passage of the gravitational wave. Now, unfortunately, this gravitational wave memory is extremely difficult to measure, but it would still be very interesting to measure at some point in some future. Now, these plots were constructed numerically at the time, but since then, analytic expressions have become available. Right. So now this is a field theory product. So how does this compare with general relativity? And the short version is that there is complete agreement, though there was a gripping story to get to that particular statement. And I see somebody here laughing, remembering. And maybe there is some further gripping story to be had, but anyway. Now, the slightly longer version of this agreement is that there is complete agreement when the field theory and the GR results are translated to the same Bondi-Metzner-Sachs frame. Now, explaining this is a longer story, but I'm going to demonstrate what I mean in QED. Right? So in QED, imagine for a second that you have a point particle, static. Its potential is given by this. So there is a piece that's, Coulomb potential is not transverse because it's not radiation escaping, it's just a static thing. Now imagine for a second that you just boost this, or you look at it from a frame that moves with some velocity v. So if you look at this, then you compute the vector potential in that new frame, you will find that there are some non-transverse pieces. But there is also a piece that's transverse and depends on the angles, and it looks very much like radiation. So where did the radiation come from? Well, it came from nowhere because, as it turns out, that radiation is pure gauge. In QED, where we typically worry only about field strengths and so on, we really don't care about this. But if we are in GR and we actually measure the analog of the vector potential, which is the metric, then we need to worry about this. And this translation basically says we need to pick exactly the same gauge as far as these large gauge transformations are concerned. So, said differently, if anybody cares to compare gauge-dependent quantities, then one better make sure that they are in the same gauge when they are compared. It's nothing particularly fancy, just that somehow hindsight is always 20/20. All right, so now this is all there is to be said as far as spinless scattering through 3 loops is concerned. So I'm going to refer to this as not particularly high loop order or not particularly high order. Especially if I decide to quantify high order by the amount of pain and suffering that is needed to get there. So to get to higher orders, one has a collection of challenges that has to have to be overcome. And in fact, the first one already appears at 3 loops. So let me start with that. And it has to do with the word essentially that I snuck in very early on, as far as scattering and bound being governed by essentially the same Hamiltonian. So in Newtonian physics, there is no issue going from bound motion to unbound motion. All you have to do is switch the sign of the energy, and there it is. And in general relativity, the same is true as far as interactions that are instantaneous is concerned, and this has been formalized to all orders in the form of the boundary to bound map. Now, unfortunately, or fortunately, if one is interested in more interesting things, general relativity also exhibits forces that are history dependent. And in fact, this is not very special to general relativity. This is a feature of essentially all theories that have self-interacting mediators, including QCD. So if one is interested in the force, if one thinks of the force as being mediated by an exchange of gravitons, as we do, and if one is interested in the force experienced by a particle at time t, then one should look back in the history of that particle and see where all these gravitons are coming from. And in a non-trivial space-time, such as the one around the black hole, one can have gravitons hitting this point at time t, essentially coming from the entire history of the particle. So the force is something like an integral over the history. And well, the history remembers at some level whether it was a bound orbit or an unbound orbit. And because of this, the Hamiltonians that we construct, they are really Hamiltonians describing hyperbolic motion, because we constructed them from scattering. So the challenge is to attempt to figure out how to construct an elliptic Hamiltonian, especially for this history-dependent forces, that out of the hyperbolic one. At the moment, we don't have a good strategy for this, but at least for now, there is a patch. There is a temporary solution which amounts to reaching back into the answer, subtracting the time non-local part or the history-dependent bit, and add it, analytically continue as in Newtonian physics, and then add for the bound motion, add the bound history-dependent forces. So one might wonder, how does this work? How well does this work? Well, it's not terribly bad. In fact, it's quite good. So here are some older plots showing how they look. So the thing to look at is the blue dashed line, which overlaps with the gray, which is the result of the effective one-body theory with pure post-Newtonian input. So they match. They are essentially on top of each other. Now, the very curious thing is what happens if one forgets that there are history-dependent forces and one tries to just take the Hamiltonian and declare, I've got the Hamiltonian, I'm not afraid to use it in any way I want. So if one does this, then one goes to the right panel and one gets the orange curve, which interestingly goes closer to numerical relativity, which is the dashed black line, than the post-Newtonian results, and as well as the results obtained by this subtraction and addition, which are captured by this by the blue lines. Exactly why that happens, we don't know. It's an interesting observation, which is encouraging, as the authors indicate. And but it's something that is worth keeping in mind, because it indicates that that these troublesome terms, or the history-dependent terms, are not particularly significant, at least as far as numerical accuracy is concerned. As a conceptual thing, they're very important, and we would like to understand them. But as far as predictions are concerned, one may be able to get around them. And indeed, this was the point of a more recent study of these guys. All right, so this is one of the challenges, and in fact, to my mind, is perhaps the main challenge. Now, there are quite a few more, and I have not spoken about spin, so I'm not going to read for you the challenges related to the spin, but I am, of course, happy to discuss them afterwards. There are also non-perturbative challenges having to do with resummation of perturbation theory. The plots that I showed you, they rely on the effective one-body theory, but there are field theory-based resummation methods that we would like to learn how to use. For example, one might want to learn how to get large angle scattering out of field theory, and as well as one might want to learn how to get other aspects of black hole physics from field theory, which both of which have to do with strong field regime. Now, about large angle scattering from field theory, that's there's a brilliant example of synergy between various approaches, which is captured by this particularly busy plot. So as it turns out, a scattering angle against a Schwarzschild black hole, for example, exhibits a singularity at a certain critical value of the impact parameter. Basically, Schwarzschild can be modeled, as far as the equations of motion are concerned, is a potential. And if you aim straight at the top of the potential, then there is a logarithmic singularity having to do with the incoming particle orbiting an infinite number of times around the black hole. So this would be, yeah. So that singularity is logarithmic, and it's a singularity that appears in the geodesic motion. It turns out that the correction to the geodesic motion also exhibits a singularity, which is stronger. It's a power-like singularity. But if one squints enough at that at the two, one notices that the two can be put together into a single logarithm, just with a shift under the in the argument of the logarithm. And this power-like singularity appears from the expansion. So with this idea in hand, these guys looked at the radiated energy, not at the scattering angle, but the radiated energy in GR, and tried to match this information at low impact parameter with post-Minkowskian information at large impact parameter. And the result is what you see here. It's the solid green line. Sorry, it's the dashed green line. And notice that it goes straight through. It goes straight through the numerical dots, which are the dots. Now, as it turns out, this interpolation improved the agreement between numerics already at large impact parameter, where post-Minkowskian perturbation theory was supposed to be valid, and it is valid, except that this fit here introduced some implicit resummation in these at large impact parameter, which improved the match. So here, the bottom panel is a characterization of the errors of the agreement with numerical relativity. So you see that it's of the order of 10 to the minus 1, actually, yeah, 10 to the minus 1. So 0.1%. So that's great. So I should say this is, like I said already, this is a great example of synergy between numerical methods, cell-force methods in this case, and quantum field theory, post-Minkowskian calculations. All right, so these are the conceptual things. I am shortly running out of time, so I will have to speed through the rest. The other challenges, they have, oops, though not through the jokes. The other challenges have to do with the current workflow for constructing observables from a field theory point of view. So in there, one picks one's favorite poison, whatever method you want, amplitudes, word line, and so on. One constructs an integrand and organizes it into integral families. Then one has to take this and reduce it to a set of master integrals and lose a few hairs in the process. And then take these master integrals and evaluate it. So I should say this reduction has to do with the fact that at this stage, one encounters millions of integrals. At this stage, one reduces the millions of integrals to thousands of integrals. Then one evaluates the master integrals, which reduces them from thousands of integrals to a small set of boundary conditions. And then one evaluates the boundary conditions, and one is happily afterwards when a result comes out and an observable comes out. So there are every stage in this chart that is not green has some issues that have to be addressed. So I will say a few words about each of them. So the algebraic challenge has to do with constructing integrands, and the analytic and computational challenges have to do with the evaluation of the resulting integrands. So I will not, just as before when I didn't show you how to compute amplitudes, I will not show you the details of any of this. But the idea is that one has to accept that as one goes to sufficiently high loop orders, one has to deal with many terms. And in fact, the number of terms grows, the number of graphs grows factorially, and the number of terms in each graph grows just because they have more and more vertices. So you know, we on our side, from an Amplitudes point of view side, we came up with a neat way of organizing this, which amounts to choosing a particularly nice basis that essentially allows us to just read terms in the integrand from directly in terms of the poles and residues of that integrand, but those poles and residues can be computed by substantially simpler means. So by and large, the algebraic challenge is under some amount of control, though it's you know, one needs a fairly big computer to deal with it at 4 and 5 loops. Now, the other bit that's that I would like to emphasize is that this method feeds back straight into particle physics and can be used not only in classical calculations, such as what we're using here, but it can be used, for example, to construct integrands for QCD amplitudes. Now, this is the construction of the integrand. The evaluation of the integrals, well, that's another game altogether. And I should stress that the caps here, they are not a typo. They are meant that way. So the idea is we have these rational functions, which are the integrands. And we need to turn them into functions that sometimes have names and sometimes they don't. At 4 loops, the kinds of integrals that we have, they have 13 propagators and some number of irreducible numerators. So all in all, they have about 22 structures that can appear under the integral sign. And the denominator has at most 13 factors. And these integrals that appear for waveforms are substantially more complex. They correspond to 5 external lines, so there is one more momentum, therefore there are more invariants. So I was mentioning what's the strategy. The idea is to first identify zeros in the form of total derivatives and junk them, and in the process reduce all these integrals to a smaller set, which are called master integrals, and then using exactly the same procedure, construct differential equations for these master integrals and evaluate them that way, up to boundary conditions. So now, as it turns out, all off the shelf, both of these are in fact automated. There are automated programs out there that can do it for you. Now, the thing is that anything that you take off the shelf is not going to work, just because the integrals are much too complex. So to get somewhere, both us and our competitors, the Humboldt group, we needed to make improvements to public codes as well as construct private ones, and as well as come up with smarter ways to speed up solving large systems of linear equations. So all in all, this happens to be sufficient to get results at 4 loops. What happens at higher orders is unclear, but I would still like to emphasize the same as I emphasized before. These methods that we needed to develop to get results in the classical physics, they feed back into particle physics and improve these codes that are actively used for QCD calculations. Now, the differential equation story is quite analogous. So this is how one constructs them. One takes derivatives of the master integrals. The result is a sum of integrals, similar to those that have already been reduced to master integrals. So one applies those tables, those reduction tables, and reduces these guys back to the same integrals up to some connection matrix here that depends on the variables and on the dimension regulator. And one has to solve this system of linear differential equations. Now, in this form, it's complicated to solve because this connection matrix has both poles in dimension regulator as well as zeros in dimension regulator, so 1 over d minus 4, and as well as positive powers of d minus 4. So solving this in this form by iteration requires iterating an infinite number of times, because one has epsilon times 1 over epsilon, and they can appear at any order in the iteration. So the preferred method, the preferred approach to solving this is to construct the so-called canonical basis. in which all this d dependence is factorized as a single factor of d minus 4. Now, it's great if this is possible, and most of the time is possible, but it is really difficult to find. So in a sense, you know, there is no really free lunch. Either it's complicated here or it's complicated to get there, but anyway, it's possible most of the time, and then whenever it's possible, everybody's happy. However, getting there turns out to be more of a mix of arts and science. So with all these preparations and with very little time left, I should say a few words about how to get to higher loops, which amounts to attacking the problem in stages, as well as embrace whatever GR can tell us, and ideally that we can also understand from field theory point of view. So one important bit is that observables, as well as S-matrix elements in the classical limit are polynomial in the symmetric mass ratio, and each coefficient of the symmetric mass ratio is gauge invariant, just because gauge transformations don't necessarily involve nu. So one could compute each p separately, and this is what we did. As well as one should attempt to learn as much as possible from simpler theories, such as QED, which is what we started with. Anyway, long story short, by the end of a couple of years, we have both us as well as the Humboldt group. We constructed the instantaneous interactions in general relativity at order g to the 5th. And the Humboldt group also has these conservative radiation effects, which is a fancy way of saying these history-dependent forces. They have the history-dependent forces. They also constructed, in very nice papers, this part of the dissipative part of the scattering, which we have not constructed yet. So all in all, it is constructing the rest of the dissipative effects is very much in the cards. However, getting to higher orders with the current methods requires careful consideration before embarking in this problem. So now I told you that we've done it, so I have to show you a plot that shows that we actually have done it. So these are plots of scattering angles, these ones, up to some coefficients. So this is I0, I1, and I2. And there's an interesting, this is, we evaluated the integrals as a series through various orders up to 44 or to 44th. And there is good convergence up to some value of velocity, and then the thing starts spreading out. It's an interesting question why it starts spreading out. The answer happens to be that there is a pole in the physical region for velocity. And the Humboldt group have a very specific value for it. It's somewhere, V.9 something. Exactly why that pole is there is anybody's guess. It could be that radiation effects will remove it, or it could be that it's there and we have to make sure that we understand why it is there. I'm afraid I cannot answer that question, but you should stay tuned. So that brings me to the last slide. I hope I convinced you that scattering amplitudes and field theory methods are a powerful approach to the two-body problem. They did advance the state of the art in the weak field regime, at least in the scattering regime. And there are many other results that I did not discuss. These methods are powerful enough to allow for future advances. And there certainly are interesting challenges, both on the conceptual side and on the practical side. And this effort also produced new tools for amplitudes and collider physics, which hopefully will spark new calculations, which will reveal new structures, and hopefully the cycle will continue repeating itself for a little while. So all in all, I think we are warranted to expect more results, both in gravitational wave physics as well as more understanding in general gravitational theories based on these methods. Thank you very much.
Questions?
Thank you. I think I lost track of what's classical and what's quantum. I'm sorry.
That was
sounds
the
dumb,
idea.
But can you summarize again?
Yes, that was the idea. This is everything that was on these slides was essentially classical.
Right.
Now, if one hands you a scattering amplitude, an integrated scattering amplitude, and says this is a scattering amplitude in the quantum theory, and a 2-to-2 scattering amplitude, and they will ask you, okay, so now out of this, extract for me what's the classical bit. The procedure is as follows. You first look at the, let me get there. You first look at the power of the coupling of Newton's constant, and you find it is n. Right? Now you reach inside that expression that they gave you, and you look for the dependence on the momentum transfer, that is this 1 over q to the 3 minus n. And if 3 minus n happens to be even, you also look for a logarithm that multiplies it. Read off the coefficient, and that's the classical answer. Now, as it turns out, doing the calculation the way I just described is a terrible idea, because one has to compute enormous amounts of stuff only to throw them out at the end. The idea is to do calculations with these methods, or by whatever methods, and aim straight to just the bits that produce this particular dependence on the momentum transfer, and this is what we did. When I showed you this Hamiltonian, it was these Hamiltonians, they were constructed in exactly that fashion. We tossed out from the outset everything that has no chance of contributing to that particular, in this case, to 1 over q square here, 1 over q here, and log of q there. And we tossed out everything else, and we focused just on those particular contributions.
So have we learned anything about a theory of quantum gravity from this? No.
No, we have not learned anything on the theory of quantum gravity, at least not yet. Other than what to expect from that theory if we took its classical limit, and we should get this, but yes.
2 questions, if you allow me. So the first question, so you're talking about 2-to-2 scattering, yes. Hamiltonian.
Yes.
The other hand side, at the very beginning you said it's very important you look for the radiation or gravitational waves out of the system.
Yes.
So the next question is, why should I look for 2-to-2, not 2-to-3, not 2-to-n? Because it seems like in your logic it should be contribution.
Yeah, so there are 2 reasons, right? So one is we do look at 2-to-3, and these plots here, they are the result of a 2-to-3 calculation. But at the moment, and certainly when this started, it was resummation was not, field theory based resummation was not on our radar. So the idea was to supply our GR friends who have methods, their own methods to resum things, to supply them with something that is useful, which is one of the ingredients that they actually need to carry out this resummation, and the Hamiltonian is one of them. Yeah. So nowadays, of course, there is efforts to compute the other pieces that they need, like fluxes and actually fluxes, energy and angular momentum. And these are. They can be phrased as still as a 2-to-2 kind of they can be phrased as an event-shaped calculation. So on the outside they still look like 2-to-2, but of course in the final state they are. It happens that they are 2-to-3 with 3 particles in the final state. More than that it turns out it's not classical.
You're not afraid of encountering different divergences as soon as you're going to 2-to-n?
Yes. Can we talk about that later? I'm happy to answer. I'm happy to answer. It was yes. So the rod infrared divergences. So it's right there. Right. So the waveform by itself is not infrared divergent. Sorry, it is infrared divergent, and one has to say something, right? Why? What is the purpose in life of those infrared divergences? As it turns out, they are gauge transformations. In this context, they are gauge transformations, and they can be removed by a coordinate redefinition, which is also conveniently or inconveniently buried in this line when translated to the same BMS frame. Now, Other infrared divergences, I should say there are several kinds of infrared divergences, and I would like to talk to you about at least some of them. Something that's more inclusive, to date we have not encountered infrared divergences. So that includes the total energy loss. That it's essentially it's the analog of the energy, one energy correlator, and that presumably it has reasons to be finite.
And if final question, so you were talking about moving order by order in Newton constant, going beyond approximation.
Mm-hmm.
But conceptually, imagine I'm going to infinite number of loops. Yeah, I know that at the end of the day, your system will scatter two massive bodies from bound state. So bound state will manifest themselves as a level of P2P expansion. Another way you expand, you have some analyticity appearing as a level of P2P expansion. Yes. Did you already see it? Because you mentioned resummation. My question is, knowing that P2P expansion will break down on a certain level, do you see any say manifestation of this phenomenon already at the level of 5 loops?
Through 5 loops, straight perturbation theory, no. One could identify some, I'm sure you know this, but in QED, if one does the Econol resummation, one can identify at some level bound states as poles in the impact parameter space. So one can, and for that, it is sufficient to resum just the ladders. Something similar can be observed here. There are poles that there are analogous poles that one finds in the Econol resummation. Now, are those all the poles? I don't know. If I were a betting person, I would say no, and certainly they would not be. The details of the poles would not be accurate. But the thing is that these bound states in GR they don't want to be stable, right? They always have to decay. So that part is certainly not included. The details of that we have not seen exactly. We have not seen at all.
More questions? Maybe one more? 2 more.
Another question. So also at some point at the beginning you mentioned post-Minkowski and post-Newtonian expansions.
Yes.
For practical purposes, for observations in the near future, is one of these 2 approaches more efficient than the other? Or
It depends exactly what you mean by efficient. So as it turns out, so one can think of the post-Minkowskian expansion as a partial resummation of the post-Newtonian expansion. One resums the velocity dependence. So the post-Newtonian expansion is a double expansion in V and an expansion in this ratio with the number of factors of each, the sum of the number of factors of each kind fixed. So if one resums the V part of the post-Newtonian expansion, then one finds the post-Minkowskian expansion. Physically, they cover different regions of parameter space. One would expect post-Minkowskian expansion to be better when, certainly better when for scattering orbits, but also for elliptic, for widely, for orbits with a large eccentricity. Just because in that case there are regions on the orbit where the velocities are large. As far as efficiency is concerned, if one had an integrand that gives you the post-Minkowskian expansion, then it is always possible to expand it and get back to the post-Newtonian expansion. But one would need, but that integrand would in fact contain all the powers of velocity. I don't know if that answers your question, but.
No, I meant just for, for instance, for LISA data.
Yes.
Will post-Newtonian expansion be sufficient, or post-Minkowski will already be there and more powerful?
Again, it depends. Okay, so for that, it depends on the source. Yeah. So if the source happens to be a binary which is quasi-circular, then post-Newtonian is sufficient. If the source is an extreme mass ratio system, then post-Minkowskian is going to be important.
And you want to be able to capture both of them, right?
Yes, ideally, yes.
I'm trying to understand how to extract waveform from this formalism. Is the idea really, like I first calculate the amplitude and map that onto Hamiltonian and still numerically solve the system, or?
So that would be one way to do it. The numerics involved is substantially simpler than solving numerical relativity. Yeah, that is one way to do it. And that approach has the advantage that it will produce a result that is resummed in the EOB sense. If one doesn't care about resummation, then one can get a waveform just by computing the one-point function of the gravitational fluctuation. And it depends how powerful one is. One can go to various loop orders. Yeah, so these plots here, they have been constructed in this second version.
Okay, let's thank Radu again.
Thank you.